You may have looked at the title of this video and said, I know how to round numbers. And you may only be watching this out of morbid curiosity to see what I have to say about rounding numbers, but I'm glad that you came in because rounding numbers can be a slightly more tricky thing than you may realize. Don't forget that every time that we accidentally create a bias in our values, we're going to be subtly tipping the scales of a measurement. And in chemistry, we've got some very subtle measurements that we've done. There's a technique called NMR, and you put a sample into a magnetic field, and a very tiny portion of those molecules will realign to follow the magnetic field. And it's going to give off a very weak radio signal when they switch back. We're talking about a very tiny signal hiding inside of a much bigger set of noise. Not a bigger set of noise, but a large set of noise. And that's one place where if you have poor rounding, you could create a bias that makes a signal where there is no signal. So let's see what our rules for rounding really are. Now, if we have a number like this, and we know that we are going to have to end up with 4 sig figs, and I've got an x here because I'm going to talk about 3 different cases in a moment. Well, the first 2 cases are going to be what you'd expect intuitively. If the number is small, so if it's less than the number 5, so 2.4662, you're going to round the number down to be 2.466. That's exactly what you expected, I'm sure. If it's more than 5, you're going to round it up. So if this were 2.4666, we'd round that up to be 2.467. Again, that's exactly what you'd expect. What happens if the very last place of your value happens to be equal to 5 and doesn't have any decimal places after it? If it has decimal places after it, it's either going to be more than 5 or less than 5, right? So we wouldn't have any confusion there. But if the last value you've got in your calculation is a 5, what do? To take the bias away, we're always going to round to the even number. So in this case, the value happens to be 2.466. So we would write 2.466 for our final answer. We wouldn't round it up to the 7 because 7 would be our odd number. Slightly complicated, but not very bad. And notice how it took the entire decision out of our hands. That's the idea. We want it to be as random as the flip of a coin. In fact, hopefully more random than the flip of a coin. There could be a tiny bias in that one too. Now, we don't round until the very last step of our entire problem. That's when we do all of our rounding. We'll retain extra values the entire time. Now, if you've got a 17-digit value on your calculator, I'm not saying you have to type all 17 digits each time. Check your sig figs. Keep an extra place or 2 beyond the biggest sig fig that you're expecting, the longest sig fig you're expecting, and that will prevent you from having any accidental round-off errors. So save that until the very end. Now, here's a couple of examples. Let's just take a look at them to make sure that we understand what's going on. If you want, go ahead and pause the video right now and give these 4 a shot. Okay, so let's walk through that one. So for this first one, 1.576, it's larger than 5, so we're going to round up. That'll be 1.58. This one is 1.574. It's less than, so we're going to round it down. 1.57. Here's one where we're right there at that dividing line. 1.575. I have to make this into the even number, so this one would round to be 1.58. And the next one, for similar reasons, we're going to say, okay, we round to the even number, so this one will be 1.56. Now, in this example, notice that we've got uncertainty here in this last place, and sure enough, that's the spot where everything ends up varying. We have extra values, but those are going to be completely uncertain. Remember that this, if we're rounding to this place here, we're saying that it's the least significant value. The one that's past it is going to be the insignificant value, which is why we're rounding it out, right? That's the idea for rounding.